Alright, this is section 9.4 and 9.5 that deals with covalent bonding, orbital overlap, and then it takes a look at the hybridization of these orbitals. So the first part, section 9.4, is something that a lot of people have already assumed. So you assume that when two things come together, that their orbitals, like these are s orbitals in a hydrogen atom, they're going to overlap. And the trick is that they have to overlap just right. They can't overlap too much. They can't be too close together. They can't be too far away like this. And so I always call this kind of like a Goldilocks things. It's not too hot. It's not too cold. It's just right. So they have to overlap just at this right amount. Now, if you have something that has p orbitals that engage in bonding, then you'd have the p orbital overlap with the s orbital like this. Or if you have two chlorine molecules bonding, then you'd have the p orbitals just overlap a little bit like this. Anyway, bottom line is that orbitals overlap to form bonds, and they have to overlap just the right amount. And there's actually a nice big graph here showing you that it can't be too far apart. It's got to be just close enough right here to minimize the energy, and it can't be too close. So that's what orbital overlap is that they have to overlap just right to form a bond. Section 9.5 talks about the hybridization of orbitals. Because throughout this study of molecular shape, we've really just taken a look at bonds as being like little sticks. So we've taken carbon and hydrogen like this, and we've just said, oh, then there's this wedge coming out here like this, and there's this dash going back here like this, and we can say it's 109.5 bond angle. But we haven't really looked at the orbitals that actually come off of the hydrogen and come off of the carbon, or whatever atom we're looking at. So what kind of orbital overlap does this cause, and how does this shape orientation go into the molecular geometries? Well, it turns out that these S and P's, when they have to overlap, they'd be like a blob, like we showed right here. And so it'd be hard for it to orientate itself, and we've got all these other electrons on the inside right here. And so the electrons that undergo the bonding part actually undergo what's called hybridization. That means that the electrons in the outer valence shell, the S and P orbitals, combine. And when they combine, they're said to hybridize. And so there is one of an S kind in every valence shell. There's 3 of a P kind. And when one of each of those comes together, they form a set of what's called hybridized orbitals. If there's one S and one P, then they're going to form 2 of these sp hybrid orbitals, which end up looking like just bigger or larger p orbitals. So here's a set of sp orbitals because it's from one s and one p, and they call this sp hybridized. So now it can go and bond with others, and it can have an equal sharing of electrons, or unequal if it's non-polar. If it's polar. But these allow for the orbital overlap to take place and then to stick together really well. Well, there are 3 different kinds of this combination or hybridization. There's one where you have an S and 1 P. There's one where you have S and 2 P's. And there's one where you have S and 3 P's. And it all depends on how many bonded domains or non-bonded domains you're going to have around the particular atom that is going to do the bonding. So here are the 3. There's an sp hybridized orbital set, there's an sp2 hybridized orbital set, and there's an sp3. So don't say sp squared or sp cubed, say sp2 or sp3. So how do you tell? Well, you tell by looking at the bonded and the non-bonded domains of electrons about an atom. So look at the bonded and the non-bonded domains. So bottom line, what you have to do is be able to draw the Lewis electron dot structure. And then once you've drawn the Lewis electron dot structure, look at how they're shared. So here are a couple of examples. Here's one in the book that's exactly the same. So here is a nice breaker of the octet rule. Beryllium is known to do that and have less than 8. Ends up having 4. And then around the central atom, what we want to do is determine what is the hybridization of the s and p orbitals. So take your thumb, take your hand, hold it out right here, hold out a thumb, and this stands for S. This finger stands for P, this finger stands for P, and this finger stands for P. And so it goes S, P, P, P. Now we are able to count. And so we look at the bonded or non-bonded domain around the central atom, and the first one we encounter, we put out a thumb and we say it's S. And then we look at the second one we encounter, and we put one out and we put out a P. And remember, we count bonded and non-bonded domains, and since there's nothing else around this beryllium, it is sp hybridized. So this has an s and a p orbital that come together to form 2 hybrid orbitals that can form bonds. Let's look at this one, BF3. So thumb out, fingers out, ready to go. S, P, P. And we're only looking at the central atom right here because that's the only thing we're really interested in right now, is what is the hybridization of the orbitals inside of the boron. spp. Oh, this is sp2 hybridized because there are 3 electron domains total around the central atom. Let's look at some more. Here is a nice molecule of methane. This handsome molecule has an sp, p, P, 4 electron domains around it, so this would be sp3 hybridized, sp3. Remember, your thumb always starts first, and that's the S, and then you have a P, 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 depending on how many bonded or non-bonded domains there are. So here, let's get into some tricky ones. Now let's look at NH3, some ammonia right here, okay? Nitrogen to hydrogen would be an S, P, P, and you have to count the non-bonded domain too, so this guy's not left out. That would be another P. Even though it's not bonded, it would be hybridized, and so this would be an sp3 hybridized molecule. 2 more. Let's look at ones with double bonds and unshared pairs of electrons. This is going to get crazy. So here is carbon, and we're going to look around carbon, and we're going to look only at the bonded and non-bonded domains around carbon. Remember, an electron domain can be a single, double, or triple bond, or an unshared pair of electrons. So this is an S, this is a P. That's it. That's all that's around the carbon. So this is an sp hybridized set of orbitals for carbon. All right, how about this SO3 molecule right here? Start here, S, P, P. All right, so that would have an S and 2 P's, so this would be sp2 hybridized. Somebody might be concerned because they noticed this double bond would resonate and move around to here, and it would actually be a bond and a third between each one. You're correct, it doesn't make any difference if it's a resonating double bond or just a double bond. You still just count it once. So this would be an sp2 hybridized set of orbitals. All right, good luck with hybridizing your orbitals and counting them out.